So now we go to our last speaker in this session. So we have Dr. Rene Claveria. Rene is an assistant professor at the Department of Environmental Science at Ateneo de Manila University. He is a geologist by profession and has worked in different capacities in government, mining industry, and now in academia. He received his doctorate at the University of the Philippines in economic geology as his field of specialization. His areas of expertise are in mineral exploration, mining geology, petrology, and ore microscopy. I can say that we've managed to make him into a biologist with the association that we've had in the last 10 years. His present researches are on phytoremediation and phytomining, and on trace and rare earth element geochemistry. So thank you very much, Rene. So I think you have to unmute yourself. Rene,
okay.
Yeah, okay.
Yeah, thank you, Job. Good morning. Thank you very much for the very nice introduction. Allow me to share screen now. Sorry.
Yes, I can see your PowerPoint, so you can just maximize it.
Yeah.
Presentation view.
Yeah.
Okay, great. Thank you.
Okay, I got it. Let me move to the first slide. Okay, can everybody see the slides?
Yes, looks good, Doxy.
It's okay. Okay, what I'm going to present now is actually part of a research project on phytotechnologies funded by PSHERD. This is a collaboration among researchers like Dr. Tess Perez, Dr. Agustin Doronila, Dr. Ayan Navarrete, Ms. Sofia Dairit, Mr. Brian Lim, Ms. Elaine Perez, Dr. Dennis Apuan, and Ms. Mary Jean Apuan. The title of this presentation is Recovering Copper and Arsenic from Hyperaccumulator Ferns, Perspectives on Phytomining. Most of us are quite familiar with hyperaccumulators. These are plants that can accumulate metals into their above ground structures at values commonly above 1000 ppm and may even reach to values of about 10,000 ppm. And these plants are not affected by such accumulation. Their values are beyond the normal upper limits of plants in tolerating hyperaccumulated metals. For example, the metal copper. A hyperaccumulator can absorb 10,000, 1,000 ppm or more copper as compared to a normal plant that can absorb copper only to about 30 ppm. Otherwise, the plant would experience phytotoxicity. The general objective of the research is to determine the usefulness of hyperaccumulators. We know that they are very effective in decontaminating the soil of various metals. However, there has been a constant issue on what to do with these plants as they contain relatively high amounts of metals. These plants thrive very well and will always tend to survive in contaminated soils, as these areas are practically their natural habitat. Harvesting and disposing them may even be an added problem. The thought of recovering the metals from the plants would be an interest to most of us. Apparently, this has been done elsewhere. I would like to cite the work of Brooks et al. 1999 on the concept of phytomining, where hyperaccumulators can be used to extract metals from soils that were left behind by conventional mining due to their sub-economic grade. A very good example is in nickel-ferrous laterite mining, where conventional mining tend to extract laterite or do not tend to extract laterite with grades below 2%, as this is already considered as sub-economical. Hyperaccumulators, as mentioned by Job a while ago, can absorb nickel from these sub-economical soils up to 6%. So in essence, we might as well mine these nickel hyperaccumulators. We made an assessment on the different kinds of hyperaccumulators that can efficiently absorb copper and arsenic, and of which will be used in our metal recovery processes. In Benguet, in a small-scale mining area at Camp 6 along Cannon Road, we noted the abundance of Pyrogramma calomilanus, and in an old tailings pond of Benguet Corporation, we noted also the abundance of Pteris vittata. These ferns are well studied and are known to be excellent arsenic hyperaccumulators. We confirm this by their high translocation factor values, indicating higher concentration of arsenic in the shoots and the leaves. Going south in Surigao at Manila Mining, we observed the abundance of a new fern, Pteris milano caulon, thriving very well with Pyrogramma calomilanus and Pteris vittata. The copper analysis of the plant showed high bioaccumulation factor values with the high concentration of copper found in the roots, classifying this fern as a phytostabilizer. The arsenic content apparently showed the high translocation factor values, therefore higher concentration of arsenic found in the shoots and the leaves, therefore classifying the fern also as a arsenic hyperaccumulator. It was actually a discovery of a fern that can accumulate both copper and arsenic. After assessing other metallophytes, we took interest on the 3 ferns that can be used for our recovery experiments. These were Pteris milano caulon, Pyrogramma calomilanus, and Pteris vittata. For the recovery of copper, we used the roots of Pteris milano caulon due to their high copper concentrations. The recovery is through the electrowinning process. Electrowinning is an old traditional method used in mining and metallurgy for the removal of copper and other metals from the ores. The method is relatively simple, with the use of 2 electrodes, an anode and a cathode, and the application of current. The solution was prepared with the use of nitric acid to digest copper from the roots. Aqua regia was also used, but apparently did not indicate significant differences in dissolution process with that of nitric acid. The experiment setup has aluminum as the insoluble electrode, an acid solution laden with copper, and a variable condition such as voltage and time. From the results of the experiment, the copper in the solution was reduced drastically after the electrowinning process. This is noted at different time frames, 30 minutes, 60, and 90 minutes, as well as different currents, 1.5, 3, and 6 volts. Looking into the percent recovery, there's no significant difference with respect to recoveries ranging from 98.7 to 99%. If we are to assess efficiency, we have to consider the amount of energy used. So the most efficient conditions are with variables 30 minutes with respect to time and a current of 3 volts. For the recovery of arsenic, we use the above ground components of Pitheris vittata and Pterogramma calomilanus for their high arsenic content. The recovery process is through the hydrothermal mineralization technique. From previous studies, this method was used to remove metals from wastewater. The concept behind this method is the natural hydrothermal mineralization process. At depths of about 1 kilometer or more, magmatic and magma-heated waters circulate towards the surface. These heated waters are characteristically acidic and can dissolve metals from the surrounding bedrock. In areas where conditions change, such as lowering of temperatures and the increase of pH, with the appropriate conditions, there's a tendency of metals that are dissolved in the heated waters to precipitate and are normally manifested as veins. To mimic this, we use stainless steel vessels with thick liners. The variables to the experiment are pH and temperature. From the equation shown in the slide, to digest arsenic from the plant, nitric acid was used, and in the process have actually oxidized arsenite, As3, to arsenate, As5, which is actually the preferred arsenic species for the recovery process. The formation of arsenate should be consistent throughout the process. In the hydrothermal mineralization technique, a mineralizer is added, that of calcium hydroxide, which would increase eventually the pH of the circulating solution. At lower temperatures, it was expected that arsenic would precipitate as a solid. From the results of the experiment, the arsenic concentrations in the solution were reduced drastically, with the final pH of the solution being more basic. Apparently, arsenic was noted to precipitate as a solid. Though this initial experiment has provided us a possible tool for arsenic recovery, it is recommended that further studies be made. With some successes in the recovery of arsenic and copper, we eventually focused on applying this to ecological restoration and mine rehabilitation. The first thing we did was to propagate the potential hyperaccumulators. We were quite successful in the development of propagating protocols. With the accomplishment of propagating most of the ferns, we eventually built up nurseries to cultivate hyperaccumulators and other metallophytes for various phytoremediation studies and for mine rehabilitation. We grew most of these plants to maturity prior to transplanting them to the rehabilitation areas. We have chosen a particular site at Manila Mining in Surigao, and this is the abandoned Suyok North Copper Gold Open Pit Mine. It is relatively wide, barren area with no vegetation, except for the sporadic growth of few Pterogramma calomilanus. Using this as a reference, we decided to transplant Pterogramma calomilanus from the nursery to this area. The challenge was on plant care management, as we found out that the fern is relatively sensitive to transplanting. Immediate care should be provided regularly, that of water and amendments. If not done, a large percentage of the plant would eventually die. It was really unfortunate that we were not able to do regular monitoring of the rehabilitation site. It is highly recommended that plant care should be provided and in order for us to have a successful rehabilitation activity. The presentation is quite short. I would like to thank PSHERD for funding Phytotechnologies project and the collaboration we had with LaSalle and UP Los Baños on the different related projects. It was a very successful collaboration among the three universities. As a reference, we listed some of the publications coming from the results generated from the research project. If you are interested in some of the papers, please inform us and we are most willing to provide you copies of what you need. Okay, thank you very much, and hoping this presentation has provided you information on the various applications of hyperaccumulators. I would appreciate answering questions if there are any. Thank you very much.
Great. Thank you very much, Rene. Thank you very much, Rene. I thought it was quite fascinating. It was really beyond the box. No, don't worry about the shortness, but I think you have answered a very important question that people always ask: what do you do with the biomass once you've accumulated that metals? But you know, you've demonstrated, and it's proof of concept that you can actually utilize it for some other purposes in really good cleanup. And you know, like I made that comment there, that it really is a great synergy of skills. And thank you very much. So I open the